now. It's on the Kepler mission, which is absolutely, I'd say, the most exciting scientific project going in the world today. And the four people to my right are all involved in it, and I'm not, and I'm very jealous. I'm on the SOFIA Flying Observatory program, and one of the things I do is train teachers to work with the scientists on board SOFIA. But Kepler is just fantastic. And so here we are at the last session of what's been, to my mind, wonderful conference, and so here we go with, I hope, a bit of a climax. So to my right is John Jenkins, who is the analysis lead for Kepler, which means he's oversees a group of more than 24 scientists and programmers who built the software system and maintain the software system and run the software system that digs the tiny signals of transiting planets, Earth-sized planets, out of the enormous data set that Kepler is producing, and that's heroic. An Earth-sized planet causes an 80 parts per million eclipse, or reduction in light for a few hours in the signal from a star the size of the sun, and they can pull those out. Next is Deborah Fisher, who's a professor of astronomy at Yale University. Her business is detecting planets by another technique, the radial velocity Doppler shift, star wobble technique, and often that can be employed to verify or extend the discoveries that Kepler has made, and vice versa. So it's a different side of the same business, and a very important side of it, and has been involved in Deborah has been involved in the discovery of 150 planets so far, with working with collaborators at the University of California, Carnegie Institution, and Space Telescope. One of the interesting projects that she's done is to show there's a correlation between the chemical composition of the host star and the likelihood that it shows a Jovian-sized planet. And then next is Doug Caldwell, who's the instrument scientist for Kepler, and so is intimately involved, has done a lot of the ground-based work preparing for Kepler, for instance, measuring the properties of the target stars that Kepler is looking at, which involved some amount of time at the South Pole. Was that or
not for Kepler, but
but anyway, you've been at the South Pole, and again I'm jealous. And then Martin, last but not least, Martin Still, who is in charge of the Kepler Guest Observer Office, which is for scientists to apply to use Kepler data, to Kepler observations for scientific research other than the transit planet search, for instance, properties of stars. As I understand it, when the first data came down from Kepler showing small oscillations in the brightness of stars, which were due to basically seismic vibrations inside the stars, which tells you a lot about the interiors of the stars. The astronomers were crying. The data were so beautiful, far better than anything anyone had had. So that's the kind of thing that they're doing. So what we'll do is each panelist will give their remarks, then they'll respond to each other, although I bet they're on the same page pretty much, and we won't try to manufacture controversy, and then open it up for questions from the audience. So first, John.
Thank you, Dana. So good afternoon. I'm glad to see everybody hung in there for the best talk session of the weekend, if not the conference. So I'm John Jenkins, the analysis lead, and indeed my team and I built the processing software that takes the pixels and turns them into planets, or at least planet candidates. So I want to provide you with a sort of a retrospective, or at least an overview of the Kepler mission. How many people know about the Kepler mission? And I'm not talking about the band, although they're great too. Okay, well, then I'll try to be brief with those remarks, but how many people saw the transit of Venus? Fantastic. For those of you that didn't Only 105 years to wait for the next one, but it's well worth it, I can tell you that. So it's kind of amazing. Deborah and I were on Haleakala in Maui, and I was standing there and having paid $10 to enter Haleakala Park so that I could witness this transit and compare that against the $600 million that went into Kepler to do exactly the same thing, and that is to watch these stars. In our case, we're watching a field of view that's over 100 square degrees. It's about the size of the palm of your hand, held at arm's length, to stare at these stars as continuously as possible, to observe instances when a planet in its orbit crosses in front of the disk of the star, blocking out a small fraction of the light. And this indeed is a very challenging experiment. It requires a precision on the order of 20 parts per million. This is something that you can't do from the ground, or at least nobody's been able to demonstrate it, certainly not at the time scales that are relevant for finding transits, which last from about an hour out to maybe half a day for a central Earth transit. And of course, you never know when a star is going to wink at you, so you do have to look as continuously as possible. So all of those requirements, precision, the completeness and continuation, continuity of the observations forces you to go to space to do a survey like Kepler, which is different than the radial velocity work where you can sneak peeks every so often to check out what's going on with the velocity of the star along the line of sight. But they are indeed quite complementary. So what is Kepler doing to revolutionize our picture of extrasolar planets? It's doing quite a lot, because when I was in graduate school and even afterwards, we didn't know about planets outside of the solar system, and every time that we thought there was one, it seemed to be something that got retracted. So it was quite a milestone in 1995 when the first planet around a main sequence star similar to the Sun was discovered by Mayor and Kalo. And of course, that was the start of a long succession of planets being discovered by Jeff Marcy and Deborah and others, and mainly by radial velocity. And for those first several years, there were still some naysayers, some people who questioned the authenticity or the validity of these discoveries. And it was thought, well, maybe this is something that's going on in the stars themselves. It's not a planet, or maybe these are substellar objects, but they're formed because all these things we're finding them so close to the star in orbits that you don't find in our own solar system. Maybe these objects are more like stars than they are like planets in terms of how they form. And it was not until the year 2000 when the first transiting planet was discovered that sort of put a lot of those doubts to bed. And now we have an object that we have its size and its mass, and we can start saying more things about what it is and learn more about these systems in general. But until Kepler came along, it's been a game mainly of finding planets that are closer in size to Jupiter, although efforts of Deborah and others are pushing down the sensitivity of radial velocity. I'm sure she'll talk more about that, so that we hope at some point in the future, near future, to be able to detect the masses of planets as small as Earth in much further and longer orbits than we have to date. But what Kepler has done is allow us to reach down to find planets that are much smaller than Jupiter. Most of our planets are Neptune-sized, 4 times the Earth radius or smaller. And indeed, the smaller the planet, the more prevalent the planets are. So small planets seem to be favored. It's also true that smaller stars tend to favor more smaller planets. So the cooler, smaller stars tend to have more planets than the hotter, larger stars. And we're finding planets in multiple systems. So not just not just one planet here around this star and one planet there. We're also finding multiple transiting planets in many cases. We have approximately 900 planetary candidates orbiting 366 stars. So we have doubles, triples, quadruples. One example of 6 planets transiting one star. This tells us that our picture of how planetary systems form is relatively right, and that is that they form out of collapsing protoplanetary disks that spin up as they collapse and tend to collapse into one plane, and so the orbits tend to be coplanar. So what we're learning from Kepler regarding extrasolar planets is that there is an abundance of planets. It tends to favor the smaller planets, but we do need to continue the mission in order to reach the place where we can actually find Earth-sized planets in Earth-like orbits of Sun-like stars. We've just collected a little over 3 years worth of data, and we're just at getting to the interesting part, because indeed we need several events, several transits, before we can even call it a planet candidate. So I'd like to turn over to Deborah now.
Thank you. Well, I thought there are two things that I might tell you about. First of all, the technique that I use is this Doppler technique. So the way that this works is that we watch the star. We don't see the planet at all, but what we see is that as the planet is orbiting the star, it's tugging the star around a common center of mass. So now, from our view, the planet disappears, but we see the star coming toward us and away from us. And by modeling that data, we get the mass of the planet, okay? Although we don't actually know the tilt of the orbit. Okay, with the transit technique, of course, as the planet passes in front of the star, depending on the ratio of the cross-sectional area of the planet to the cross-sectional area of the star, you get a diminution in light. And that dip, the amount that the light dips, tells you the size of the planet. So now any school kid can tell you that if you know the mass of the planet and if you know the size of the planet, you can calculate its mean density. So we've gotten a window into planets, right, that orbit stars, planets we can't even see, orbiting stars that are hundreds of light years away, and we can tell you what their density is, what their internal structure is likely to be, maybe they have an atmosphere, so the amount of science that we're getting from something that we can't even see still blows my mind. It's incredible. I'm not on the Kepler team, I'm just like a fan of the Kepler team. And then the other thing, I just recently finished a News and Views article for Nature magazine on a really cool result that came out of the Kepler data. And as Dana said, some of the work that I had done with Jeff Valente in 2005, I can't believe it's that long ago, was to establish this correlation between the chemical composition of planets and of stars, the host stars, and whether or not there were gas giant planets there. So at the time, we only care about the gas giant planets. We weren't finding any small rocky planets. So an analysis that was done, led by Lars Buchov and Dave Latham and others, showed that the planet, this correlation with chemical composition is different for the small rocky planets. Okay, now, to understand what this means, start at the Big Bang, okay? The only elements in the periodic table that existed were hydrogen and helium, a little bit of lithium. Okay, it took generations of star formation, evolution, death, okay, to seed the galaxy with the heavier elements, the stuff that we're made out of. And so we wondered when we saw this correlation between metallicity and planets, wow, maybe planet formation is a relatively recent phenomenon. You know, the first stars in the galaxy in the universe couldn't have formed planets. Stars now, in the last, say 4 or 5 billion years do. Does that mean that there aren't any civilizations that are 10 billion years old? So, again, the planets had to wait until the stars had manufactured iron and carbon and so forth. So the cool thing about this new result is that for the smaller planets, there isn't such a strong correlation. In fact, there's not a measurable boundary. The stars have a whole range. They're compared to the sun, metal poor. Astronomers call everything except hydrogen and helium metals, by the way. So they're metal poor all the way up to metal rich. So they span a wide range. That's interesting because when it comes back to this question of civilizations, it means that we didn't have to wait, right? The universe didn't have to wait quite so long to start forming small rocky planets. And so maybe it pushes back the clock for the beginning of life elsewhere. And to me, that is one of many amazing results that's come out of Kepler. Doug?
All right, so we've talked about, John introduced Kepler. One of the things that I sort of have to keep in mind working on this project, we're finding lots of very neat planets and very interesting, exciting things, but I think the topic of today's discussion was Kepler doing something with astronomy in the 21st century, revolutionizing astronomy. And I think the big thing, Kepler's sort of dry-sounding goal that was written down in 1992 or something, was to determine the frequency of Earth-sized planets in the habitable zone. And the key word there, I think, is frequency. We're not looking for one planet like the Earth that's orbiting at the right distance from its star to have water. We're trying to determine how common or rare these things are. And that's the real sort of revolution of Kepler. It's not a single targeted search looking at one star. It's trying to look at a lot of stars and find this frequency. So we're really trying to get at the statistics of planets. And I know that Deborah and the Doppler survey groups had been doing this, and they started getting lots of good results. But Kepler's sort of the next step in that. It's a survey of 170,000 stars, but it's really only looking in one sort of relatively small patch of the sky. So it would be nice to have other surveys continue this type of work. And that's sort of the other big advantage of Kepler is it's this survey. We're looking at a lot of stars that we didn't necessarily know, what much detail about them, but we're looking at them, and we're looking at them continuously. Every 30 minutes we get a data point on these stars for 3 years now, and hopefully going on for 7.5 years. And we almost never look away. It's very, we're observing them something like 90% of the time. And it's a lot of the other things that we'll find that we didn't intend to look for, I think that'll be very interesting. And I know Martin will probably talk about some of those other things that weren't planned. But I think that's probably one of the big steps in astronomy in the 21st century is these large surveys and huge data sets that are going to come out, starting to come out now. I mean, Kepler's, it seems kind of huge to us, but it's really a baby compared to some of the surveys that are coming online. There's this LSST survey, which is, I just heard a talk, they're going to take something like 3 terabytes an hour of data while they're observing. That's a lot. It makes Kepler look small even, by a lot. So I think it's this idea of doing surveys. They have some goals as what they want to find, but they don't know what they're going to find around all these stars. And what we're finding with Kepler is we didn't either, and we're finding lots of new and exciting things. And I think that's sort of astronomy in the 21st century. So I'll let Martin take it.
Thank you. I'm not the most observant guy in the world, but what I did observe is that all 3 of my loved colleagues, maybe beside Doug a little bit, have avoided the title of this session, is how will Kepler change science for the 21st century? And it's a perfectly natural thing to do, because what an impossible question, what a dastardly title to put up there. And I can't help thinking about when I was a kid. Growing up in England, there was only 2 TV channels to watch. And on Thursday night, you either watched ITV for Coronation Street, which was either the best or worst soap opera in the world, and still is. And on the other side, there was a program called Tomorrow's World, which every Thursday tried to predict what the future, what everyday life would be like, whether we were driving hover cars or eating canned ice cream and things like that. It's really sad to see now, 30 to 40 years later, it's now just an item of fun on YouTube, how wrong they got it week after week. And even now, I have a book at my bookcase at home, which is predicting what science will be like 50 years from now. And it was written 10 years ago, and it's still incredibly wrong. It's still going in the wrong direction. Even 10 years ago, people were not predicting all of the innovations in science and everyday life that we feel today. I grew up watching Star Trek, and I was so jealous of tricorders, and I was watching Space 1999, and they were talking to each other through little gadgets they kept in their pockets. I thought, I couldn't wait, but they got that right. I have a little gadget in my pocket. That's so awesome. But so it's the same here. The big answer here is none of us can project forward, can extrapolate to the end of the 21st century and answer how Kepler will change our lives and our understanding of the universe. It's just too far ahead. What we can do is extrapolate what we know into the future, but only a few years into the future. And there's a whole different bunch of science which Kepler is able to tackle completely serendipitously. It was never intended to do anything other than an exoplanet survey. There was no concessions in the design to do something slightly different and something not quite as important, but really interesting. You got what you got. And yet, if you look at the papers that are being produced by the scientific community, they are dominated by work and science which is not necessarily directly related to exoplanet discovery or characterization. They are dominated by stellar astrophysics. The people who are interested in studying the physics of stars are finding Kepler to be by far the most unique and powerful telescope they have used for a long, long time, and it is revolutionizing stellar astrophysics. All stars vary. Kepler monitors and characterizes that variability. All stars, believe it or not, ring like bells. Some people call it the music of the spheres, but to be quite honest, it is bloody awful. When people, as John has done, have made sound files, oh my God, it drives me up the wall. I think of it more like bell ringing, but the tone and the frequency and the pitch of those bells tells you how big those stars are, how hot they are, what their composition is, what the stratified layers, how they behave with each other, what's in the core of those stars. We can actually look into the very center of stars just by extrapolating the effect that acoustic waves have and gravity waves have as they extrapolate out to the surface of those stars, and Kepler can detect them, can detect those changes, and these things are changing in parts per million over time, and Kepler is able to detect this and characterize those stars. This is something we've only ever really been able to do for the sun and a few of the brightest stars in our neighborhood. Kepler can do it for thousands, tens of thousands of stars all at the same time. We are understanding the galactic stellar zoo in a way that we've never understood it before. We can detect amazing things going on in binary stars. 50% of all stars in the universe have a partner, have a star that they are mutually, they're orbiting a mutual center of gravity. These are great because when they orbit each other and when they eclipse each other, you can actually measure their sizes, their masses, and all their other properties in a completely different way. There's two ways to measure stars down to a precision that we've never had before. Now, this is not just great for stars. This is great for understanding the planets around those stars. The only way right now we have of measuring the sizes of those planets is by using the transits, measuring the width and depth of those transits, and using that information to determine how large those planets are, but relative to the size of the stars. It's a relative number always. And we have to know more about that star in order to put an absolute hard number on the size of that planet. So the better we know the size of the star, the better we know the size of the planet. The exoplanet program would be nowhere without the stellar astrophysics that everybody else is doing with Kepler. We also need to know the temperature of the star, because depending on the distance the planet is from the star and the temperature of the star, that tells you, or gives you an idea what the surface temperature of that star is. Now, you have to wave your hands a little bit because you don't know what kind of atmosphere that planet has. You don't know how much light is getting through, how much light is being absorbed and retained. But you can get some handle on what we call the equilibrium temperature is on the surface of that planet. And of course, what we're looking for are those planets which have a solid surface, but also have the right surface temperature to retain liquid water. That is the golden ticket as far as Kepler is concerned. And one more thing, other than stars, you can go even further afield. There are many astronomers that are interested in extragalactic astronomy. They're interested in what's going on outside our own galaxy, what's going on in other galaxies in the universe, half a universe away. Kepler, because it's observing the same field, the same part of the sky, so far for 3 years, and we have a mission extension, yay, which is going to mean we're going to observe for at least another 4 years. That'll be 7.5 years worth of data at least. We're observing galaxies with 30-minute cadence, with very few data gaps. This is completely unique, and the extragalactic community are, excuse my language, having wet dreams about this right now. Because using that information, they can do a whole bunch of things. Most importantly, they can use the way that the center, the cores of these galaxies are varying over time. These are the central supermassive black holes inside these galaxies, they can actually measure the sizes of these black holes, and they can measure the way stars and other material and gas is actually interacting and falling into those black holes, which is awesome. Anyway, I've talked for far too long, so over to Dana.
Well, let me ask, I think this first question is for John and Doug in some combination. I think the folks here would like some takeaways, even in round numbers, of Kepler's status so far. And one of the buzzwords here is confirmed planets versus candidate planets. You might understand that you have to see 3 transits at least with an equal period, an equal spacing in time, before you know that that was really a planet and not something else. So how many confirmed planets do you have versus candidate planets as of June 24th? And round numbers are okay. Here he is. He's right in there. Go. What's the right number?
Well, Michelle will correct us if we're wrong. I think we went up to, are we at 72 now, Michelle? 74, okay. I was on vacation. I'm sorry. So we have 74 confirmed planets. When we say it's a confirmed planet, it means that we have a very high confidence that it indeed is a planet. We have over 2326 right now, planetary candidates. And these are basically candidate planets because while we've identified the signatures of the planets in the data, and we've done everything possible to exclude the possibility that these events are being caused by, for example, a background eclipsing binary that's diluted by the brighter target star so that its eclipses look like planetary transit. We haven't got sufficient complementary evidence to bring our confidence level high enough to call those things planets. But we do believe that something on the order of 80% or more of these planetary candidates are indeed bona fide planets, and our vetting procedures are getting better all the time. So in some sense, the newer the planet candidate, the more reliable it is.
So you're saying 80% of those 2,300 you're as a guess will be confirmed as planets, something like that.
Well, something like that. I think that's conservative, but it's also true that we have so many candidates, it may be that not all of them will ever able to be confirmed, right? I mean, we won't be able to confirm every single one. For one thing, some of them are around stars that are too dim to do some of the observations that we'd really like. So we have to rely on statistical arguments to transition them from candidate to planet.
Okay, but the 76 confirmed, it seems like a low number after 3 years, but there's many, many hundreds ready to pop into the confirmed category soon.
That's basically true. Now, I told you earlier that we have approximately 900 planetary candidates that are in multiple transiting planet systems where the orbital alignment is such that you see the orbital planes nearly edge on so that multiple planets are transiting. And in those cases, the statistics tell you that you have a much higher confidence level that those systems are planetary systems, even though at something like the 90+% confidence level, even though if you talk about an individual planetary candidate in one of those systems, that might not be the case.
Yeah, I think that, Dana, that's a couple of the really exciting things coming out of Kepler was the number of multiple planet systems we found. And I need Michelle again, but I think we've got over 900 systems, or is it planets in systems?
Planets in
systems
yeah.
that are in multiple systems. 900, that's a lot. That's more than 8 or 9 in our solar system. And these things are common. There are definitely lots of stars out there with more than one planet. And the other exciting thing we're finding is that the peak of our planet distribution now, based on our analysis we've done so far, is planets that are around 2 Earth radii. We don't have any planets like that in our solar system. They're between the size of the Earth and Neptune. So there's this large population of planets that we don't really know much about based on our solar system, and they're very common, and it's cool to see that it's a new kind of thing we can learn about.
You have one 6-planet system, right? Or is it more than one?
I think just one.
Okay, so one system with 6 confirmed planets in it, yeah, and confirmed because the planets interact, and so we can watch the interaction. How many candidates in habitable zones?
The latest release paper that came out in February listed, I think, the final version was either 42 or 46 planet candidates in the habitable zone. Habitable zone's a little squishy, because a lot of people define it in different ways.
Wishy-washy.
Yeah, wishy-washy. And how much water. So depending on what you decide, what temperature means habitable zone, which the selection we chose in the paper, which I think was 180 to 303 or something degrees Kelvin, which doesn't make much sense to most people, around 0 C,
280.
gave you like 42 planets in the habitable zone. And we're refining that as we go, because one of the things we find out, as Martin mentioned, we have sort of guesses as to what our stars are when we're looking at them, but we often have errors in those guesses, and it so oftentimes turns out that the star was bigger than we thought, or smaller than we thought, or hotter than we thought, or cooler. So when we first find a planet, we say, oh, look, it's an Earth-sized planet in the habitable zone, and then we get better measurements on the star. We say, oh, the star is actually twice as big as we thought, so the planet's really twice Earth-size, and it's hotter, so it's really not in the habitable zone. So as we get more information about these things, these numbers all shift around.
But of the, so 40-some-odd candidates that are in some definition of a habitable zone liquid water temperature, what's the smallest of those in size relative to Earth?
It's a little bit smaller than Earth.
Yeah.
The smallest candidate is somewhat smaller, but comparable to the size of the Earth.
That deserves all of our applause. Now, when Deborah was talking about the compositions of the parent stars, and she talked about how the Big Bang started out with hydrogen and helium, we have good evidence of that. The oldest stars that we detect are just hydrogen and helium, so on. There's a point that went flying by there that I expect you make a big deal out of in introductory astronomy when you teach it, and I do too at Santa Clara and at Stanford and you and at Yale, which is the oxygen you're breathing, the carbon in your bodies, the nitrogen in the air, the calcium in your bones, those atoms were made in red giant stars. That's where they come from, right? That generations before the sun. That's the only place, hot enough to make oxygen and calcium and carbon. That's where, and there wasn't any of that early in the history of the universe, as Deborah said, and there's more as time goes on because stars make it. And elements beyond 26, beyond iron, which includes gold and silver and platinum, are made in supernova explosions. If you have gold, those atoms were made in an exploding star, period. That's the only place where gold comes from. That's where gold's made. So that's, when I teach introductory astronomy, that's a big, that's the money line right there, and thought that we should, sort of stop and share that for a second. Yeah, but so tell your friends if you have gold, it's from a supernova explosion. That's where gold comes from, period. So, and then I wonder, Martin, some of the data that you get from the seismology actually tells the age of the stars, right? Which we didn't have, and that's an astrobiology primo point, isn't it?
That's right. I would say the situation is far more healthier than that, though, because the age requires an incredible amount of precision from these pulsations. And so there's probably only going to be of order 100 to 1,000 of those stars that you can actually age by a pulsation. But the good news is Kepler's better than that. You can also age a star by its rotation rate. The older a star is, the slower it rotates. Now, some old stars rotate really fast because they're in binaries and their companion spins them up really fast. But those stars which are on their own, single stars, the older they are, the slower they go. They lose their angular momentum. just because they have winds, they're losing material into the interstellar medium around those stars, and that takes a lot of that spin energy away as they get older. So there are very few instruments in the world that can observe stars for the length of time required. We're talking about observing stars between, a few hours to months or years to actually measure their rotation rates. And you have to observe them with incredible precision. And in that sense, there's nothing quite like Kepler for doing this. So Kepler is not only going to calibrate using some standard stars in its field, where it knows how old they are. It's going to calibrate how fast stars rotate from anywhere between a few 100 million years old to 7 or 8 thousand million years old. And remember, the sun is 4,500 million years old. So there's going to be tens of thousands of stars in that field that Kepler, or the people working upon Kepler data, are going to be able to age those stars. Now that's fantastic, because it's not only aging the stars. By assumption, you assume that the planets formed at the same time as the parent star. So you're also saying how old the planets are. And we know it took 4.5 billion years for the human race to develop on planet Earth. I have no idea how long it would take other intelligent things to develop on other planets, but it gives you another measurement. It gives you another yardstick to what you're looking at. If you're looking at a young planet, chances are life hasn't developed on that yet. You look at a planet a few thousand million years old, that's probably the kind of thing that we're looking at, the kind of planet we're looking at, to see a mirror of ourselves, something where life has developed in a similar way.
Kepler people turn over their Earth size, well, maybe not Earth size, but temperate zone planets to the SETI Institute's listening program at the Allen Telescope Array. And a fellow sitting next to me last night at a banquet had on his iPad showing what the Allen Array was looking at last night while we were eating, and there were 2 Kepler stars with Earth candidates around them. So that, within weeks of them becoming candidates and being identified, then the listening program is adding them to its search list. So that's that's a wonderful place to be, to have the 2 programs talking to each other. So I wonder if the 4 panelists had questions or responses to each other, or violent agreement, or
We know each other so well. We argue with each other day in, day out. I think it's more fair just to hand it over to the room and let them argue with us.
I was going to pull up greatest hits from the sound files for Martin's benefit, but I'll leave that for later.
so questions. And is there a runner with a microphone?
They just line up, I think.
Okay. Oh, well, we have microphone there.
You said that Kepler samples the brightness every half hour. Whenever we've had a couple of transits, we know when the next one is probably coming. Is there any usefulness in upping the sample rate then? Or can it even do that?
Well, there's some utility for some kinds of objects if you have very short transits because you've got a short period planet, or you have very deep transits and you want, or high sensitivity, you want to time the transits. But we do have a program that allows us to sample the brightness of up to 512 stars at 1 minute cadence, and that's a very precious resource that Martin argues should go all to astrophysics. But indeed, using these 1 minute samples allows us to better characterize and have greater time resolution on the details of the shapes of the transits, and that helps us in several ways. It helps with the oscillations, because if you can measure oscillations, The asteroseismology can tell you more about the star, and it tells you more about the planet, but also it allows you to make better timing measurements of the transits themselves. And Dana alluded to this, and that is that in many of the multiple systems, the planets are in non-Keplerian orbit, so they're not just going along following Kepler's laws. They're actually interacting with each other gravitationally, so they're tugging on each other. One is slowing down because it's giving up some energy to another that's speeding up. So the transits, rather than coming as, just like this, some of them get slower and others are speeding up. And you can then take these transit timing variations and either place upper limits or actually estimate the masses of the planets directly from the Kepler data themselves. And that's what happened with Kepler 11, which is this system of 6 planets, the 5 innermost of which are all within the orbit of Mercury, if you held it up against the solar system, the outer of which is within the orbit of Venus. But the 5 innermost planets are interacting so that you can see these variations. The outer one, it may be interacting gravitationally, but it's far enough from the innermost 5 that we can't measure any changes in its arrival times of its transits. So this is proving to be a rather powerful technique to extend what we know about the planets simply through the Kepler data, especially for objects, stars that are too dim to do radio velocity work. And it will help us discriminate between rocky worlds and water worlds. And that's one of the greatest mysteries still left, I think, in the sense that we talk about what the future is. Just because a planet is 1.5 Earth radii, it doesn't mean that it's made out of rock. And so we have a large number now of these super Earths, and super Earth sounds great. That's a place everybody would want to go live. Superman lives there, right? But indeed, these super Earths may be quite different, much more like mini Neptunes in places where it might be hard for us to imagine intelligent life taking hold because there's no rocky surface to walk around on. So transit timing variations and advances in radial velocity precision will both help us discriminate between rocky and non-rocky worlds and understand where the transition is between rocky worlds like Earth and water worlds.
There's another awesome application for observing transits with this 1 minute, very rare, very precious 1 minute cadence that we have. And that is, we can observe the transits of the planets in front of star spots on the surfaces of those stars. Now that's kind of cool and great, but what it does allow us to do is measure the angle of inclination between, say, the rotation of the star and the orbit of the planet. So we can, in those particular examples, we can see how inclined planets are relative to other planets in the system and the star itself. Just like our own Pluto has a much more inclined orbit to the rest of the planets in the ecliptic. In fact, some of the extreme examples, the most extreme one I think we have is a gas giant which is actually orbiting in the opposite sense to the rotation of the star. And all that means is that there is some kind of cosmic billiards going on in many of these systems where planets and other objects in these systems are actually interacting with each other, and they're being ejected, and they're migrating inwards and outwards within these systems. And so you're seeing these planets jockey for position inside these systems. And it's observational evidence of a phenomenon which has been theorized for quite some time, and it's a thing of beauty to see.
My question was going to be, can you detect sunspot activity on these stars? I think you just answered that.
Yes.
And how do you tell the difference, though, between planets going around the star as opposed to it's just a sunspot rotating with the star?
Well, the main difference between star spots and transits is the time scale of the phenomena. So a star like the sun is rotating once on average every 27 days. And so it takes a couple of weeks for a spot to actually cross from one side to the other, and it gives you a change in brightness that's about 1,000 parts per million, and that indeed is deeper than an Earth-sized transit. But it's happening over a time scale that's much longer than a transit duration, which again, actually the mean transit duration for the Earth from somewhere random, if you're seeing the Earth transit, is 10 hours. So that's the main means by which we can separate the two in terms of having the sensitivity. The other thing is that spots evolve and change. So if you look at solar data, you will never see the same spot signature twice, even though it's the same spot or spot group, because spots evolve and change latitude and change their size over time scales that are comparable to the rotation period of the sun. Whereas transits, unless you're talking about systems where you have significant transit timing variations, have a very high degree of coherence. So the transit is very periodic. It's happening exactly every 15 point something days, and it's very regular, and the duration is very regular as well.
Can I just ask how you physically keep all that data? Where do you put it? I mean, it's got to be a lot of books.
We actually, unfortunately, throw most of it away on the spacecraft. We have a 95 megapixel digital camera that we're using basically, and we take an image of the full field every 6 seconds and add it for 30 minutes, and then we throw away 90 million of the pixels, and we keep about 5 million pixels precisely because we can't store it all on the spacecraft and we can't transmit it all down. So that's why we had to select this 170,000 stars. That's basically a spacecraft limitation. So that's not all that much data, especially compared to some of these other surveys. But right now we keep it at NASA Ames in a locked room.
And the archive, the archive, Doug, that you never have to worry about is at MAST. So it's at the Mikulski, and I've forgotten what the rest of the new acronym is. Archive at the Mikulski Archive at the Space Telescope. And Martin can say a lot more about that, but anybody can get Kepler data. You can sign up for a free account, download the data as FITS files or as tarballs of FITS files. Planet Hunters actually has a really nice interface, and they host, Deborah can speak about this, host the Kepler light curves, and any one of you can sign up, become a Planet Hunter, and look for transits in the Kepler data. And with the extended mission, and this makes Martin proud, I'm sure, it's going to become a completely open mission in the sense that as soon as our software gets done processing and generating the latest data set, as soon as it hits the archive, it becomes public. So it's a very even playing field for the extended mission.
Well, I said this yesterday, and I'll say it again. If you weren't in the session, John and Doug are exactly right. And if you've got your pens available, the URL to grab all of the Kepler data is archive.stsci.edu/Kepler. And come and ask me again if you didn't get that down. Now, the important point here is, yes, it's an even playing field, but anybody can go away, anybody can use planethunters.org to eyeball individual light curves and find transits and planet candidates that our own fantastic pipeline has missed. And it's because our fantastic pipeline is trying to detect transits in as many stars as possible, as efficiently as possible. It's completely different to looking at an individual light curve and saying, there it is. It's a completely different process. So there are many different ways of skinning this cat, and we have just one way. And it's your opportunity as the scientific community and the great American public to go away and find your own planets and planet candidates before we do, which is awesome. But we need you to do it. We need you to do it because we need to understand what we are missing in our pipeline, because we cannot put a number on the Earth-sized planets in the habitable zones around other stars unless we understand how many we missed and why we missed them. And we ain't going to understand that unless you tell us where they are and what their nature is. So we desperately need you to go away and do this.
So regarding the future of Kepler, what happens in 4 years? Is there a Kepler 2? And if, depending on budget, what should we be doing with Kepler? Should we be having much more sky survey, or what would you like to see?
I'm sure my friends will add to this, but I think there are two answers. One is Kepler itself. Kepler is doing awesome science. It's extremely successful, and it will continue to do awesome science for some years to come. But there is a finite life to Kepler. There are consumables on board, specifically propellant, fuel, that maintains the spacecraft pointing. And as soon as it runs out of fuel, we won't be able to maintain that pointing at the Kepler field. The spacecraft will drift, and we won't be able to point it anymore. Mission over. And that will probably happen. It's a 10, 11 year, done 3 years, 8 years from now, roughly.
Yeah.
So maybe 2020 is the absolute end of the Kepler mission. And as you rightly point out, it also depends on NASA funding and public funding through NASA. So we managed to get a 4-year extension to 2016. And in 2014, we have to go through the whole process again every 2 years to convince NASA that we have a good scientific program and we continue to be valuable. And I have great confidence that we're going to do that. So I'm going to predict 2020 is when Kepler stops. But beyond Kepler, you then have to decide what the next thing to do. Kepler's great strength is a statistical survey, finding thousands of planets and planet candidates. But in order to do that with one simply designed telescope like we have, you had to choose the field very carefully. We have lots of stars, but they are damn faint, which means they're not necessarily, generally, the best stars to go away for SETI to look at, for other telescopes to look at and characterize their atmospheres, to look for radial velocity variations. So one argument is you need a Kepler-2 to look at brighter stars, to look for the planets with, where you can get far higher precision with other instruments. And there is such a plan. There is a Phase A study. It's called Phase A. There's a few $1 million thrown at TESS to do that. But then there's also a counter-argument that perhaps we have enough planets now, both through Kepler and all of the other endeavors going on in the exoplanet community. We have enough objects now to look at them in finer detail, say do spectroscopy of those planetary atmospheres. And there is indeed another spacecraft in that Phase A study competing directly with TESS called Finesse to do exactly that. And so I believe that decision will be made in the next 6 to 12 months. John may know
The
more.
concept study reports are due in September, and I would hope that they would get the word out towards the end of the year or beginning of 13, because the money's supposed to start flowing in March of 13.
So NASA will choose really soon what it will do. More surveys or more detailed observations of the planets that we know.
And of course, one of the main reasons why Kepler was chosen in the first place was to establish the depth that one would have to look with a system like Terrestrial Planet Finder, which would seek to actually image individual planets, to do spectroscopy, to look for biosignatures, to start studying the seasonal variations in the rotation period and day and night cycles by watching the variation of the light coming off of the planet. And unfortunately, we're in a position now where Terrestrial Planet Finder has sort of fallen off the edge of the planning table. And I don't know, I just think that the question of is there life out there, are there other worlds like Earth, is so important and compelling that we'll find ways to make something like TPF happen, even if it happens in a way that's completely different from the 3 architectures that have been proposed. Deborah, maybe you can say something about that.
Well, I'm kind of worried about astronomy for the next decade, actually, because the funding situation has been so dire. But it'll be, whether it's in the next 5 to 10 years or whether it's 10 to 20 years, there's no question, I think, that one of the next NASA flagship missions is going to be a mission that's going to try to get information about the atmospheres of nearby planets and see if there's life there.
So the confirmed planet less than the size of the Earth, do you have an actual estimate of the mass also, so that you can tell that it's rocky or not?
Well, if I recall the picture, we have a handful of planets that are similar to size of the Earth, for which we have masses. There's Cairo 7b, which is about 1.5 Earth radii. I can't remember offhand exactly how massive it is, but we're talking about something like 6 or 8 Earth masses. Is that about right? Kepler 10b, which is Kepler's first rocky planet, is 1.4 Earth radii and 5 or 6 Earth masses, about 8.8 grams per cubic centimeter. So both of those objects have probably compositions that are rocky. Oh, not habitable. I'm sorry. The question was habitable. Well, right now we don't. Kepler does not have a confirmed planet that's Earth size for which we have the mass that's in the habitable zone. So it's really at this stage of the game we have 3 years of data under our belt. We need 3 or more transits in order to really call it a planet, unless there's extraordinary complementary evidence. We wouldn't expect to be here today claiming that we have a large number of Earth-size, Earth mass planets in the habitable zone. That's to come.
Has there been any plans to do what Kepler's doing to the closer stars like Alpha Centauri and Barnard Star and so on and so forth?
Well, you guys can all answer this question, but yeah, there are ground-based surveys that aren't as sensitive, but then there are some missions that have been proposed and are in, as Martin said, Phase A. TESS is a survey that would look at nearby stars. There's the MOST satellite, which is already up and is looking at stars for transit, specific target stars. But I think that's going to be one of the big focuses of the next decade, because these are missions that you can build that are faster, better, cheaper, and now that we've got these statistical results from Kepler, can really make inroads.
We have time for one more question, if there is one.
I have a second. Given I don't see your name, but you mentioned the tremendous variety of side effect science from Kepler as well as the main. Is anybody giving any hints to the Swedish Academy of Sciences in the last few years what they should be looking at?
Sorry, what was the last bit? Have you sent any emails to
Yeah,
King Gustav yet?
where's your Nobel Prize, guys?
My tux doesn't fit anymore. I mean, I think that's as we go into the 21st century more, that is one of the things that as Martin mentioned, some of the things that are coming out of Kepler, but we're learning these great new things about stars, about the planets around them that we didn't really expect. And I think, sort of in summary, like he said, that we don't know the most exciting discoveries that are going to come out of Kepler probably. And we know some that we think are going to be really exciting, which is the frequency of Earth-sized planets and all this. But I'm sure there'll be things that we didn't expect at all that are going to come out.
I think, say it another way, we are not as smart as sometimes we'd like to be. And that many of the great things which have come out of Kepler, sorry guys, many of the great things that have come out of Kepler were not our ideas. They were other astronomers around the world at other institutions who saw an opportunity to try something new, some innovation that they were hoping to, they thought about 10, 20 years ago or just last week, where getting all kinds of crazy things that we never dreamt of. We're having people see the effects of Einstein's special relativity and light curves of binary stars orbiting really close to each other. As the stars approach you, they get brighter, and as they move away from you, they get fainter. This was predicted by Einstein in 1905, and we see it in other objects. But to see it with Kepler, to see special relativity at work with Kepler. Did anybody predict that? No way. It's just awesome. And just to see these wonderful innovations just suddenly show up in the scientific literature, in press releases or in journals, is incredibly rewarding. I absolutely love it. And I swear there's going to be many, many more to come, but I am not smart enough myself to tell you what they are. I can't wait for the smart people to come up with them.
Last question, sir.
Will Kepler be able to find any moons?
There's a fellow named David Kipping who's developed a quite sophisticated search algorithm whose name escapes me right now. But his aim is to find moons in the Kepler data, and his claim is that we have the sensitivity to find large moons. That's a very demanding task because unlike planets transiting solitary stars, you can't. It's not a simple signature to find. But yeah, the moon's moving around, so it's always in a different place. It's even harder than the case for circumbinary planets, where you can actually the parameter space is small enough that you can actually do a credible job of building an algorithm to find circumbinary planets, even though the signature changes with each orbit.
So somebody's working on it. Well, let's thank our panelists. And thank you. All right. And that's the end.
All right, thanks.
Cocktail.
Yes.